So if you've ever taken a calculus class before, you've probably had to deal with optimization problems. You're given a physical constraint, like only 52 meters of fence, and you're supposed to build a pen for your sheep. And of course, being a loving owner that you are, you want to give your sheep the most room to move around, so you have to maximize the area of this pen. So we'll just speed through the rest of the problem to give you the solutions. So optimization has a lot to do with calculus of variations. Though with calculus of variations, you can deals with minimizing many different things, not just area or distance. You can do time as well. Okay. So with calculus of variation, though, you're dealing with functionals, which are functions, like in this case s of gamma, which spit out a real number. Their inputs are also functions. So in this case, s of gamma, you're dealing with the definite integral from two input values, say t1 and t2 in this case, of the integrand function, which has three specific inputs or parameters. The first being t, and then gamma, where gamma is a function of t, and then gamma prime, where it's the derivative of gamma. So for minimizing or maximizing this functional, the integrand becomes very important. So in order to minimize or maximize these functionals, we have to use something called the Euler-Lagrange equation. Okay, the Euler-Lagrange equation is a way of finding critical points, similar to what we did with the sheep earlier, where you set derivatives equal to 0. In this case, you're taking the partial derivative of the integrand function, big F, with respect to gamma, minus the derivative with respect to t of the partial derivative of the integrand function, big F, but this time with respect to gamma prime. And you're setting all of that equal to 0. This will give you your minimum function, or maximum function. So while at first this may seem really complicated, let's see how it works out with an example that we all know the answer to, such as the minimum distance between any two given points. Intuitively, we know that the shortest distance between A and B would be a straight line. But for instance, there are many other functions that connect A to B. For instance, you could have this lovely little squiggle, or you could have this lovely squiggle. And how do we really know that the shortest one is the straight line? Okay, so given all of these possible functions, we need to find a way to relate to them and find the minimum distance, the minimum function that connects A and B. So given this example function from A to B, how can we find the functional, an equation that finds the distance of it? So basically what we do is let's focus in on one small segment. And by zooming in on an infinitesimally small segment, it's basically a straight line. So by zooming in on a small segment of this function, we can find the length L of the small segment by relating the x and y components. We know from Pythagorean theorem that it's equal to the square root of the change in x squared plus change in y squared. So by manipulating this equation, using the mean value theorem, we get the following equation for the length of any small segment of our function. So this is the equation of the distance of the length of any small segment. Okay, so that equation gives you the length of any small segment. So to find the length of the entire curve, all you have to do is take the sum of all the small segments. So we can take the integral from the endpoints a, b, the definite integral from a to b, of square root of 1 plus the derivative of f of x squared with respect to x. And that'll give you the length of any curve. So this is the functional that we're dealing with. So this equation basically gives you the length of any curve connecting A and B. So now we're going to change up the variables. And basically substitute, instead of f prime of x, we'll use gamma prime of t. We'll just change up the variables here. So you see here, this is a functional relating all possible functions that could connect A and B and comparing their lengths. So now we'll use the Euler-Lagrange equation So let's plug in f into the Euler-Lagrange equation for our situation. Okay, so focus on the first part. If you notice here, we're taking the derivative with respect to gamma. However, on our integrand function, radical 1 plus gamma prime squared, there is no gamma. So that means that the derivative is simply 0. Okay, so multiply both sides by -1 to get the following. Notice we're just left with the right side. So from here, let's focus on just the inner part, the derivative with respect to gamma prime of radical 1 plus gamma prime squared. So this is just a normal derivative. So we're left with 1/2 times 1 plus gamma prime squared to the -1/2 power times 2 gamma prime. And all of that equals 0. So let's simplify this a little bit. Cancel out 1/2 times 2. We're left with the derivative with respect to t of gamma prime over radical 1 plus gamma prime squared. All that equals 0. So in this case, when would the derivative of any function equal 0? Well, when it's constant. So we know that gamma prime divided by radical 1 plus gamma prime squared has to equal some constant. So after algebraic manipulation, you're left with this. Okay, so squaring both sides, we get a constant, we can eliminate that root. And that just leaves us with c squared, a constant squared is just another constant. Distributing that constant, we get the following. Okay, so since the square root of any constant just gives you another constant. So gamma prime is equal to a constant. Now, the only way that gamma prime would ever equal a constant would be if gamma were a straight line. Now, changing this into more familiar notation, mx plus b, you'll notice that the solution is linear. Okay, so the shortest distance from any points a and b in the Euclidean plane is indeed a straight line. So as you see, using the Euler-Lagrange equation does give us a solution that matches our intuition, namely that the shortest distance between any points a and b is indeed a straight line. Now this was an easy question. This was an easy equation because you only had one variable. What if we throw time into the equation? This is a classic problem that drove the creation of calculus of variations. It's called the brachistochrone problem. Brachistos meaning shortest, and chrome meaning time. Okay, so given 2 points, A and B in a vertical plane, what is the curve traced out by a point, acted on only by gravity, which starts at A and reaches B in the shortest time? So this parametric equation that we found is actually the equation for the cycloid. So the cycloid is the curve you get when you have a point on a circle, you let the circle roll, and you follow that point. Let's look at a more accurate diagram of the cycloid. More accurate depiction. Does this curve look familiar? Anyway, when you take a segment of this and invert it, you get the curve that minimizes the time between any 2 points. Now this has been a lot of abstract math, but let's see what it looks like in real life. So in the first demonstration, we'll show the brachistochrone problem. Okay, so when we solved for the minimum distance, we found that a straight line was the minimum distance. So you might be asking yourselves, why isn't this also the curve that minimizes time? So we're going to do a demonstration that shows that the cycloid is indeed a shorter time. Now that you've seen that the cycloid is indeed the solution to the brachistochrone problem, we'll show you another fun fact about the cycloid. It's also the solution to the tautochrone problem. So the tautochrone problem is basically the problem to find the curve where the time taken by an object sliding down the curve without friction, with gravity as its only force, is independent of starting point. So in other words, purple, green, and blue will all arrive at point B at the same time. So when Lagrange, one of the mathematicians who developed the Euler-Lagrange equation, solved the tautochrone problem, he sent it to Euler, and they both got really excited about it and kept corresponding, and this ultimately led to the development of calculus of variations.
Hey, I'm Sven, and I'm a violent person. Okay, and the thing is I go, oh, hi, I'm Sven.